Very good. Very good. Well, I'll join other speakers and thank you, the organizers, especially Vishnu for all his very hard work in bringing us to this wonderful place, and the previous speakers for all their wonderful talks. And I also asked the previous speakers to not remember that I asked all these obnoxious questions. Now would be a good time to realize. So, at any rate, I will tell you about something that is now for something completely different, very retro, not all the modern things, although it is motivated by some of all the modern things. So just a brief perspective. This is what I just could think about in 2 seconds. What are the black holes in string theory kind of subjects? What a lot of things these days that appear on the archive and what we've heard a lot about are things like microscopic entropies, supersymmetric indices come up, localization, that sort of thing. Black hole information paradox, or just black hole information, entanglement, complexity. We've heard talks about all these different things. But the thing that has been conspicuously absent is just a plain and simple, actual black holes. Space-time properties, stuff like that. And it's, I guess, because it's just too low value. That's why it's embarrassing I talk about these things, because that's where I'm heading, is that, what are the space-time properties? And I think most people think that, no, that's trivial. It's in the paper. Some people that I don't know because they've written it's in the papers. Well, try to find the papers. It actually turns out often that even the relatively simple questions about the black hole, the space-time properties, have not been worked out. Which is why, of course, it's a great idea to ask your students, why don't you just work out these simple space-time properties, because they are so simple. And it turns out, I know the answer. They are not so simple. That is why it has not been done. So I will here pursue just one direction of inquiry that pertains just to supergravity type of solutions. And I would like to understand what is called the attractor mechanism for BPS black holes, supersymmetry only, engage supergravity. Because I don't expect necessarily people come from different directions to know what I mean by attractor mechanism. It's an old story, but it is set in the setting of BPS black holes, or actually more generally extreme, but let's just say it's BPS. For ungauge supergravity, the Earth is completely understood, and so on. And I'll review a bit that old story so that you can see this is where we're coming from, and the implication when people are saying attractor mechanism for gauge supergravity is that it's something like that. Even though details, as I say, are not actually worked out, but people are saying it probably generalized. Well, there's some obvious differences between even posing the problem. So when you actually get to think about it, that's why I'm going to review what it used to be in the ungauged supergravity case, is that, oh no, these are completely different. If at all, there is one in the gauge supergravity case. And then I'll go and develop a few features, entropy function, and some conserved charges. Again, very retro stuff, a few extra things that are relevant for understanding, hopefully in the end, that gauge supergravity attractor story sort of completely, because we kind of need it, and I'll explain why that is. But so generally what the attractor story is think about a black hole as kind of a domain wall. That is kind of a radial evolution from some stuff at infinity, and then complicated stuff happens in the middle, and then gets to the horizon. And think about the stuff at infinity, which are really infinity, not even infinity plus 1 over r, but sort of flat space or whatever. That's a maximally symmetric space, surely supersymmetric, whatever, stuff like that. The horizon, also actually locally flat, or maybe locally, yes, very, very simple. The thing in the middle interpolates between two maximally symmetric vacua, and that is actually what we often call a domain wall. So the radial evolution is some kind of domain wall. So they're highly symmetric asymptotics in the two directions, and this domain wall is what we would like to try to understand. It's the radial dependence, so that's an important quantity. And just say that right afterwards, but yeah, at any rate, I should say that it's an important quantity in the context of ADS supergravity. We can say that radial evolution is actually what we call, renormalization group flow, and in that context, that would be one motivation for surely we should understand such things. Now, how is the horizon stuff, the infrared, related to the UV stuff? And certainly, when we say it's a renormalization group flow, You say, well, it's probably not completely trivial that we just sort of identify things. We probably have some work to do. Something happened, I was too slow. So, for the purpose of this talk, I will just talk about n equal 2 supergravity in 5 dimensions. So in n equal 2 supergravity, I'll remind you that, well, there's gravity and the superpartners, and the superpartners in particular include a gravity photon, just a single vector field. It's a vector field that doesn't have a scalar partner because the gravity multiplet does not have any scalars. And then I have n equal 2 vectors, which has gauge fields, of course, and it has a real scalar partner because 5 dimensions, there are 3 degrees of freedom in the gauge field of 1 real scalar. So that's the multiplet. And the only thing I really want to say about the matter content is that let me remind you of the counting, that there's a number of scalars and there's a number of vectors, but there's one extra vector. So therefore, they're not exactly partnered up. There's this one extra vector. And a nice way to think about that is that the scalars here, let's actually add extra scalar as if that they are equally many, and as vectors and scalars, but make the x's projective in such a way that they're just defined modular overall scale, and that way we get beautiful formulae where everything is completely covariant under relations between vector fields and scalar fields. And then in the end, you should probably fix this projective thing. For example, you might wish to take some pre-potential equal to 1, but I will not generally do that. This is sort of standard counting. But that is why we will be able to just ask ourselves about covariant questions. But so, what is the standard story in ungauged supergravity? Well, in ungauged supergravity, these scalars x, they're moduli. That means that, as I say at infinity, real infinity, where we say, oh, the solution is really simple, it's flat space. Yes, that's true, but that's not the entire solution. It's flat space with some scalars that take constant values. Which constant values? That's what it means that the moduli have broken spontaneously their symmetry or whatever. They take a particular value at infinity. It's not all that important which value it is, but they do take some value. So there's a geometry plus some value. All right? Then also near infinity, we have some data that tells us as we go inwards in sort of what direction in field space do we go. That's where we parameterize things in terms of things like the mass. And for a BPS object, the mass is in fact related to the charges. It's roughly speaking the sum of the charges. So that's a very simple formula. The mass itself is not really needed. But it is relevant to say, well, the mass is essentially the sum of charges. Yeah, but essentially, look, they're not even covariant here. There must be something there. That's the moduli. So if I were to change the moduli, the exact mass would in fact change. So as I move around in moduli space, these black holes really do change. Right? So that's my asymptotic data, and near asymptotic data that tells me how do I move inwards. Right? So it's a well-defined problem. You kind of have constants, first derivatives, now go solve your differential equations. And what the attractor mechanism says is that it happens, somewhat mysteriously at some level, I guess, that the horizon values where the scalars end up when you solve these differential equations, they end up with some value, and it's independent on where they started. That's not entirely trivial. The interpretation is that the black hole interior somehow is entirely independent of the coupling constant, because these moduli are in fact coupling constants. Some of them may be literally coupling constants. Others, they're kind of just effectively coupling constant, Yukawa, stuff like that. So these coupling constants, here there's no indices or anything like that. So this is just sort of one of the very crude ways of saying, I might be able to understand the near horizon region without understanding the far away stuff particularly well, because it's simply independent of a lot of things that it might be nice, for example, to just go to a limit where the coupling is very free. It's very simple, because since things are dependent anyway, why not? There's a bonus that is sort of the additional part of the attractor mechanism. The true attractor is this. There's an independence of initial data. But think mechanical system that has a certain set of initial data, and it ends up somewhere that has fewer data. There's a bonus that the attractor flow is what tells me how does it happen, the asymptotic data, how does it flow on the way in, and therefore give me a clear way of where do I end up. Yes?
this function, the horizon values, if you think of the function of these modular at infinity, is that a piecewise constant function, constant function?
Well, it's constant. They're independent.
So it's not like in different chambers with different attractors.
Yeah. So of course there's a more elaborate thing, and it was Gabriel was asked about it. So you're talking about horizon. There could be some wall crossing phenomena, whatever. Actually, in 5 dimensions, nope. But and besides, I'm going to consider one center.
Okay.
Pretend things are radial or whatever. There are plenty of elaborations of the story.
Yeah.
As I'd say, short also rotation, higher curvature, but for pedagogical purposes, I'm just going to create a solution. But yes, that complication I think is actually not interesting. 5 dimensions. Correct me on that, but I don't think it's so interesting. It's sort of the interplay between Q and J, the P and Q, that then has an angular momentum as well in 4 dimensions and in 5 dimensions, Q's. So at any rate, this flow then that tells us how do I get from infinity and inwards is very nice. It's actually controlled by the central charge. The central charge now is something that's really a little bit more like a central charge in quote unquote, because I'm not necessarily claiming that there's an actual algebra for which this thing here is the central charge. I'm just saying that this z here was kind of the mass. It was the sum of the charges weighed by the scalars. Then as the scalars move, I get some other kind of mass. And one way to understand the attractor mechanism is that the mass is then kind of changing as we go inwards, and at the horizon is minimal. So it's like probing energy kind of flowing down to lower energy, and then once it's minimum, it's at the horizon. So that's a very appealing picture. It doesn't quite fit in every single detail, but it's a very appealing picture if these x's here themselves cycles and something like Yao or whatever stuff like that, will probe around and find it. Indeed, I'm going to show you just a little bit more details here. Let's suppose the geometry is just this radium symmetric black hole. The F here is some function of the radius. The only reason I actually picked a 9 element is because I thought we should have it with one of the black holes what we have. And that R here is a particular definition of what R is, and it's the radial flow. And then what I'm saying is that when the central charge here flows in a particular way, by flows I mean radial dependence, and radial dependence turns out to depend on the radial dependence of the scalars in such a manner that it's explicitly positive definite. That's what I was just saying, that there is a simple relation here. This Z here, it has to be positive derivative because as R gets smaller and smaller and smaller, it goes to the minimum at the horizon. So that tells me already something about, Z is the minimum at the horizon. What is the value? The value of the entry. So in fact, even from data at infinity, what was my structure of my moduli space, what are my charges? I can find the entropy without ever even finding a macro solution, by just using these general principles. And furthermore, minimization of the moduli space, so taking this Z here, minimizing the moduli space, you get after values. This is a very general story. I told you about EPS. There's a related version of just extremal, not necessarily supersymmetric. I can have rotation. I can have R-squared corrections. Not all of these things are pretty simple. It means it will work. But the words I'm saying basically generalize to all these different cases. And I believe this is good point for questions. Just on the ungated supergravity, this is completely historical. Some of it 25 years old, generalization is not quite pretty clear. So this is pretty clear, right? But I figure not necessarily ungated. So what the real story is, well, why don't we go to gated supergravity? Just another Lagrange, why don't we do the massive DMS and call it ABS instead? And we have some fall off that encodes the black hole quantum numbers, and we can now say, that's what is known as the UV behavior. The UV is the ABS plus the fall off telling us which state in set ABS are you interested in. And the flow then will be some kind of repackaging of the data, the way the conversation always does. It's something at infinity, but it might get repackaged and be something different at the horizon that's sort of equivalent, but it's equivalent in the sense of having force grain somehow. That's these outstanding CT story. So the horizon geometry, we can itself analyze, and we can then say, well, there has to be something near the horizon. The final approach to the horizon is the Schwarzschild theory that we've been talking about. It's the IR behavior, and the final approach is kind of the, not the least development operators, and they're disappearing at that point. So what we'd like to know is, what is the fate of the attractor mechanism for ungauge supergravity? It surely would be nice to have answers that are really general to this in a broad context. I would like that. And you won't get it. But that is sort of the setup. And people are, in fact, advertising in various papers and so on the gauge attractor mechanism of gauge supergravity, and some people might even have the impression that there was such a thing. But if there was, that would be an answer to this, and you would get partial answers, but not full. In fact, first of all, I must say, ADS5 Actua, how does it look? Well, let's just think about it at infinity. Again, I have a infinite black hole in. Gauge supergravity has some scalars, and we can think about them as the exact same scalars that I had in my ungauge story, except now it's engaged, and that means that there's a potential for set scalars that depend on the superpotential. I'm going to, in this talk, just consider Fayet-Yakov's gauging, so therefore my gauge theory is going to be just taking one to number of vector multiplets, well, plus one, gauge theory plus one, or whatever. And in that case, things are really exceptionally simple. The superpotential is just linear. That's what Fayet-Yakov's parameters do in the superpotential. And therefore, this extremization problem is extremely simple. It's not something that has any structure or anything. What are the extremization conditions? Well, I have to take the covariant derivative of W equal to 0. I'm not going to say what covariant derivatives are. You have to use scalar potential or not. And if you know, you can know how to do this. If you don't know, now it's about up to time to learn scalar potential. So, at any rate, there's some supersymmetry extremization condition that basically, instead of extremizing B, let's just extremize W itself. That's simpler. I put it equal to 0, I find a solution. And the solution is that my x's are essentially equal to these coupling constants that enter in the superpotential. It's a slight technicality in that what I actually call x's, these kind of upper index x's, well, they have some partners that are lower index x's that are actually quadratics in these upper index x's. If you go into these kind of things, the relation is 2 cycles versus 4 cycles inside of Colloquium, but I'm not really going to distinguish in therapy. Again, if you know Taylor geometry, you would know how to. If you don't, you will do it peacefully later on. And what we have is basically, we have a bunch of coupling constants. How many? Well, as many as the values of I. And x's, they take what value of infinity? They take those values that are the coupling constants. So they start out as specific values, not some arbitrary values. There is no modular space. So in that sense, we know from the very beginning that there is no attractive mechanism of gauge supergravity, because we don't start out with this arbitrariness that then somehow could end up with something fixed before we even start the problem. So, well, they're fixed already. How could they possibly get more fixed? So the asymptotic values are fixed by the theory. For those who are counting, remember that the I index does have some redundancy in it, so actually it's not quite true that there are as many x's as there are c's. There's kind of one more c than there's x's, and that fixes the size of the as well. So that's one of the various parameters. So there are equally many parameters at infinity as there are, loose parameters in my ADS5 gauge theory. Just my ADS5 supergravity. And what then happens at the horizon? Well, the scalar values become functions of x's. They were already, and that never disappears. One could have imagined that dependence of what theory we're in would somehow not matter for the horizon. But if you imagine that would be true. The horizon will simply have some function of the q's and x's. So there is no attractor mechanism, at least in this kind of supergravity. The scalars depend on all asymptotic data, including what the x's were at infinity. in a certain sense, maybe you should be happy about this. You should say, oh, actually, this means that we're much more closer to ordinary mechanics. I have, I have sort of my x's and my x dots at infinity, and then I have a mechanical problem, and that was the initial conditions, and well, please go and find my final conditions. It's a standard mechanical problem, and there are as many initial values as there are final values. It's not actually, in a way, it's much more satisfying than the attractor problem. On the other hand, you might say, oh, but actually our G loop, is that not exactly when you lose information? No, not here. There is as much information in the end as there is in the beginning. Doesn't mean that I easily know how to figure out what x's are and how they get there. There could be interesting things, but this is the structure of the problem, and it's different from what it would have been in the ungaged case. So, let's, questions here?
The potentials don't have any flat directions at all, so
No.
some redundancy.
I mean, of course, I can make C's different, the same, and fine-tune, and therefore I can produce a little bit of flat direction, but that way I will get a flat direction in infinity that's mirrored by a similar flat direction at the horizon, so it really isn't, I can play a little bit around with the story, but really with the story, this is representative. What I say is not quite correct, is more.
But one thing they have in common with the ungaged ones is that there are still first order flow equations for the modular case.
There are?
Yeah.
In the gauge supergravity case?
Oh yeah, certainly. So in 4 dimensions, this was first worked out by John Vito.
Yeah,
and,
I know.
Niecki.
Yes,
And
I'm
this
very
is
aware.
5 dimensions as well.
5 dimensions. Yeah.
First order flow equations. First order flow equations for getting the profiles of the scalar physics.
Now I have to remember again, what was it that they didn't do? I'm aware, of course, of those flow equations. They even call it attractor. That's right.
This I don't remember now.
Yes, no, they definitely call it attractor mechanism, but it is confusing. Well, what several people do, including them, I believe, is that it's confusing in that if you take all these c's equal to 1, you might think that something got attracted, and it didn't. I'm aware of those flow.
My comment was just about the first order flow equations.
Yeah, no, I'm just getting a little bit confused because I think I have forgotten about them. We're about to write this stuff up. At least as where we at. So I have to remind myself what exactly they did. It's a while ago I looked at it. So, at any rate, the common version nowadays of attacking this problem is actually going a step back and not thinking about the full radial behavior. And instead say, look, I don't really care. I just want to know where I'm ending up. And for that, there's a quick story related, in fact, to the alias 2 Zen story with quantum corrections or whatnot that we heard about earlier. But the basic part of that is what is known as the entropy extremization story. What is that? What the highlight is that you find what is called the entropy function. What is that? Well, you do end up near the horizon something that's an alias 2 plus something. There may be some fucking fibering and whatnot, but it's basically an alias 2. If you evaluate the Lagrangian density on the alias 2, then since alias 2 is homogeneous, you basically get a number. It's obviously proportional to the volume of the alias 2, but otherwise you pretty much get a number, and it depends on all continuous parameters. And the extremization then of the entropy extremization proceeds by saying once I have my entropy function, the extremization determines all the continuous parameters at the horizon by just extraizing. So therefore you can find out where do I end up from this entropy function. It's kind of reminiscent of how the central charge allowed you to figure out what all the scalars were at the horizon in the ungaged case, but here the entropy function is something that's kind of like the square of the central charge. It's a more elaborate, construct. But anyway, you can construct, from this entropy function, you can extremize, find the values of the continuous parameters where we end up. In other words, you can find the IR aspects of your theory, just by knowing the theory, not having understood necessarily the flow, and you can figure out what the black hole entropy is as function of other horizon parameters. not necessarily the parameters at infinity. There are some important differences then, which I already sort of said, but do notice that the entropy extremization, which is what I think most sort of students have learned the last 10 years or so, is starting point is horizon geometry, as in starting point is IR, and then output also IR. That's very different from what was called an attractor flow in the ungazed case. Another difference is that here actually what really matters is that the black holes are extreme, because you're not trying to do the trick with the first order equations and trying to actually get sort of the square root, having to just extremize a superpotential instead of extremizing an actual potential. Here you really formulate it as extremizing the actual potential. Supersymmetry plays no role. It also does mean that the entropy extremization mechanism is, well, it's more general, but it's also more clunky to implement. There are details, technical details, so that's one of the reasons we've actually still ended up spending quite a bit of time looking through these things. Again, even though they have been done all sorts of places in literature, but yeah, well, we have to reproduce everything. You have to preserve the entire ADS2 symmetry. Now, how could you possibly miss it? Well, for example, you could miss it by putting things in a gauge where you missed some of the ADS2 symmetry, and after all, you have a gauge field that you might put in, say, oh, it doesn't even matter, it's just a field strength that has to be consistent with the ADS2 symmetry. Well, that would be wrong. One of the other things is that you have to make sure that you should be the microcanonical ensemble. That too is part and parcel of what the Saint was preaching, but some authors seem to forget that we should fix Q and J and so on. And in order to do that is that we should put in appropriate Wilson lines that would effectively correspond to a Lejano transform that says, look, if you're not already in an ensemble defined by your Q's and J's, if you have some, chemical potentials of some sort, no good, go to another ensemble where this is true. If you have angular momenta in your system, then your life will be tough. But you still have to preserve the ADS2 symmetry. And what people often do is that they reduce down to 4 dimensions, and that's at least what the Ascent paper, written, in fact, the Ascent paper of the quotation one here includes Kevin, quite well known paper, and something's read, and several other people, but at any rate, it's at least one person from this. Maybe there was another person as well. At any rate, that's the angular momentum story, that you have to, in order to preserve supersymmetries, you have to just work harder. In 5 dimensions, we have Chern-Simons terms. That's an extra pain that also is something that, well, some people get right and some don't. What's the principle? The principle is that the Chern-Simons terms, they mess things up. You must add extra terms in such a way that your equations of motion make the bulk flux conserved. This makes sense, because what you're trying to do here is that you're trying to do something just at the horizon, and yet you're claiming that you get some information about infinity. How did you encode that? By making sure you have the right boundary terms, but that's another technicality. But with all those things here, then we're all good, and we can in fact include higher curvature corrections, corner corrections, and whatnot. So the entropy function formalism, I would say, is what many people do, and I'm just emphasizing it doesn't include the flow. It doesn't include an actual UV component, and we would like that as well. So the entropy function formalism is a great tool. There's some challenges. You have high parameters here. They are continuous parameters, and the formalism said, should we extremize? They're continuous after all. Well, no. We should extremize over continuous parameters of the solution. We should not extremize of the continuous parameters of the theory. It's an important distinction here in that since these Fayiliopoulos parameters were effectively the values of the scalars at infinity, you might say, oh, they're just some kind of parameters that I should extremize over, they look continuous to me, but you should not. They're part of your theory. Another technicality is that since here, I'm talking about supersymmetric black holes. Supersymmetric black holes, painfully as it is, they must rotate. So you must deal with rotation. This is not something you just do to torture your students, although that too. But here, you really have to take care of this. So And then finally, there's also this annoying thing that the supersymmetric black holes, they actually simply only exist when the various charges which are specified in infinity is satisfy a certain constraint. If this constraint here is not satisfied, it's a completely obscure constraint. I'm writing it just so you can see that, yeah, that looks very penetrable, and it certainly is. It's not something that has any intuitive content, and tripart, including us, giving it some intuitive content, but really haven't managed to. But the fact of the matter is that to the best of our understanding, those in the community, being ours here, this constraint here must, in fact, be satisfied, or else these externalization conditions just don't have solutions. They're runaway. So the goal would be at any rate within the externalization formalism, before we get to the flow, is to externalize the entropy function, and then later, let's study the attractor flow. But first, let's see where we end. Are there any questions? So, what one is being asked to do by the entropy externalization formalism is that we need a near horizon. Yep.
I'll ask a question. To go back, you just said that you have to have rotation, right?
I have to have rotation, yes.
If I look at the last equation, I switch off J.
Yes.
Are you telling me that there was no solution of this for a continuous given the set of charges Q? I switch off J.
So if I try to switch off J, this has no solutions now.
Pardon?
This has no solutions now.
If I switch off J,
Yeah.
even
Well, I mean, technically it has something like the Q's go negative or something like that, but then since the mass was actually here, so you get negative masses and stuff like that. So there's no physics. Yeah, the J equals 0 here turns into a solution, into an equation that just doesn't have solutions. No good. I mean, it's true that that's not entirely obvious, but this thing to the other side is it's some kind of in this case, of course, it's a cubic equation, so that's also annoying. So you don't just eyeball it, but it's a pretty simple inequality that, oh, I can't find solutions. And I should notice that these Q's here I have assumed somehow satisfy suitable positivity conditions in such a manner that the mass is possible.
What is the minimal value of J for which it starts finding solutions?
That is a good question. Yeah, it's some function for Q's. That's a good question. Yeah, I don't. I didn't see that, even though I definitely work out what it is. That's a good question. But not sure. That's a very good question. So, what one actually wants to do here is to understand the geometry. So by geometries, we have 3 parameters, obscure names, my notation here, but the upshot is that you have an ADS2, you have to have such a part. In this case here, since I actually consider just a single angular momentum, in ADS5, you have some kind of 2-sphere, and how big is the 2-sphere is another number. Everything here is just numbers, it's not functions, but how big is that 2-sphere, how big is the ADS2, and then you have an extra circle that includes the rotation, so the rotation has some angular velocity, that is 0 here, and then you have some squashing parameter, in that your last circle, it might generally not have the same size as the sphere. If U2 and U1 are the same, there's no rotation, this would be a 3-sphere. In actual fact, it's sort of a co-rotating 3-sphere that then gets squashed a bit, and therefore the output of the entropy externalization would be, oh, how much does it get squashed as function of how much it rotates, as function of very charged, and stuff like that. So that's a geometrical question that you ask, just within the horizon story. There's no bar dependence, but it's still a little bit non-trivial. You know, how much squashing is there, and stuff like that, what do the scalars end up to be. And one of the things that might trick you up is that when you have the scalars, of course, they can also have some gauge fields. The gauge fields certainly have electric fields. They're kind of stand-ins for the electric charges. If the electric field has a certain value, then by Gaussian type integrals, you have the corresponding charge. But they're also magnetic fields. That's a bit tricky And the tricky thing about it, well, why do I need these things here? I can't have, with this topology, any kind of conserved magnetic charges. This is true, you cannot. So these are kind of redundant, but they're not trivial. When you have electric fields and rotation, then you also get magnetic fields. And in fact, you can't really find a frame where everything is kind of really nice. So the key here, yeah, that is just there to annoy. It's a magnetic field. Is one that doesn't itself carry independent charges, but it does, carry stuff. So if you want to find a solution, you have to figure out all of these different things. So the electric fields, the angular velocity here, these are the ones that you can think about as potentials for Q and J. You were instructed that Q and J should be kept fixed. So here I've already violated the conditions. I've written it as a function of various potentials. I shouldn't have. I should have fixed my charges, not my potentials. So I erred, but at least this was the way to actually present the geometry. So what you get is that what you should do is that you should take the Lagrangian of the solution I just took, that I just wrote down as a function of all the various continuous parameters, but then you should remember to the Lagrange transform and say, oh yeah, the conserved charges are the dual parameters to the Lagrangian. So therefore, if I take the Lagrangian, differentiate with respect to the electric field, either the one that corresponds to angular momentum or the one that corresponds to Q. When I do that, then I plug it back into the Lagrangian. My Lagrange transform is no longer the actual Lagrangian. I've turned on some extra homogeneous terms, and it is that function after the Lagrange transform that is called the entropy function. So this S here is not the action. It really is supposed to be the entropy. And as you would imagine, with a relatively complicated ansatz and Chern-Simons terms and gauge supergravity or whatever, it's I think fair to say, unilluminated. But it is at any rate very explicit. And do remember that the reason people actually like things like this, and some people like them, I'm not among them, but is that it is just a problem of extremizing over numbers. Right? This is not a function. So you just have to go into algebraic equations. Go differentiate to your heart's content, and then over V and do 1 and whatever, and then once you find the extremum, you will figure out how much electric field has been induced, how much magnetic field has been induced, how much squashing happened as function of angular momentum and whatnot. So there's some actual sort of mechanical data in there. So that's the output. Figure out what is the near horizon geometry, what are the magnetic fields, what are the scalars, go and externalize. Right. But, couldn't we somehow simplify this? Well, let me first say that actually here I just copied the very same equation that is still unilluminating. But one of the things you should extremize over is this parameter called V. V was not just any old parameter. It was the scale of ADS2. ADS2 is of course infinitely big, but we gave an extra sort of variable with how big is ADS2, some proportionality constant. Where does V actually come in? Well, you will see that after we have the Lagrange transform, this term, in fact, every single term is proportional to V. Therefore, extremizing over V is really simple. It's a Lagrange multiplier. All of the terms become 0 once we extremize over V, except the first one that, strategically speaking, are made equal to 1. Therefore, the extremum of the entropy function gives just this stuff out in front. And in fact, you may recall, or if you don't, this is my geometry. My geometry was such that I had a sphere with size U1 and this extra circle with size U2. This is, in fact, the area. So we're on the right track, just extremizing over V, which is the size of ADS, gives you the entropy. This actually is always the case, that somehow the size of ADS2 is dual to the entropy. It's what happens in all these various examples in all dimensions and so on, so that's nice. Of course, it doesn't really help you much, because now you still say, well, these functions, what are they? Well, there's some sizes. Okay, good, but that's not what I wanted. I want to figure out what those sizes are as function of charges. And if I were to know that, I could figure out what the entropy is. So we're not done, but this at least shows that, well, we're on a good track here. So what do you do next? Well, we had a bunch of vectors. The vectors are the magnetic fields and the scalars. You can extremize with respect to them, reorganize, and you get, well, magnetic fields. And you get scalar fields. Why do I show you such formulae like this? Well, for one thing to tell you, they're kind of complicated. And these are rather short, not been found before, by the way, but not that we actually really think that this is important news. But also, they depend on the C's and Q's, right? This is what I had pre-advertised. Might it possibly be that the C's drop out or something like that? Well, no, they don't. They don't. Okay, so there you go. You know, maybe you weren't very excited about learning that, as I already told you, but no, they don't simplify. And this is really the sort of core of the attractor story in the gauge case, is that, since parameters didn't disappear, well, the opposite of parameters disappearing is that things depend on all parameters. And that's much harder. So this is why some of these various things were not computed in as much detail. Technical comment, I'm going to use notations in the following slides that sometimes are completely inconsistent. Q's and C's is what I kind of had. Well, actually, these Q's here have dimension of length. N is the corresponding quantum number. On the other hand, C's, I think, did not. And the C tildes here are dimensionless. So you will sometimes see N and Q tilde, whatever, just don't bother. But as you do this, you get rid of that 5, and I might then introduce a half n squared. Think about even these integers and the n squared as just supergravity parameters. I'm not pretending at all that this is something to do with super young bills, although if it happens that I want to go to the dual theory, the formulae are ready to be compared. And that's because the final formulae are a little bit better to present in terms of these different things. Again, these are formulae that you don't really want to know how big is the horizon scale. It depends on everything. What is the squashing parameter? Very explicit. What is the ADS scale? Relative to the horizon scale. Again, everything depends on, well, everything. But once you do plug things in, it does in fact work out through the formula that many people have given, and since we actually do know the entire solution, we could just go in the area. But here I computed it using the extrapolation principles, going through the various painful steps, and finding an uncountable number of typos in the literature along the way, of people that did do this same extrapolation before, but with various things we are unhappy about, so that's why we would have to do it again. It took a long time for my students, and they have to rework. Oh, and yes, then there was this fact that these equations, they simply only had solutions with this thing here came up. I found various extremization conditions, and I said, oh, these actually consistent with one another. They're not, in general, they're not consistent with one another unless this is true. We haven't explored exactly what happens if this is not. What is the flow of? Well, I shouldn't say in this talk. I'm not going to do that.
Sorry, coming back to this last equation. If
Yes.
I were to switch off the gauging, I set the zeta's to 0, I switch off rotation.
If you what?
If you were to switch off the gauging, so the zetas...
The rotation. Switch off what?
The gauging.
Yes, it exceeds, yes.
Exceeds, and that's it.
Yes.
Then, and I also decide to switch off the rotation,
Yes.
because I can't. Then I would learn that the first term on the left-hand side is positive half.
Yes.
Because it's equals to s squared on the right-hand side.
Right.
So if I now turn on the gauging,
Turn on the gauge.
now I look at this equation.
Yes.
On the left-hand side, I have added a rotation, which
Yes.
is a positive term. So why do you say that I need to have rotation for this to be satisfied?
Well, I have to plug it. There's an S over here that I put in, right? So,
There's a square there. There's a square there.
so you're saying that.
And these Heliopolis things
Yeah.
are arbitrary.
But possible. Or at least the
Well,
same
I
sign
don't
as the
know.
cubes.
I don't know.
Same sign as the cubes. I mean, the mass is basically C cube, CQ, whatever. So each of them in order to have positive contribution, the QI and the CI of the same kind have to have the same sign.
But be that as it may, I mean, the left-hand side is positive, by the argument I've just used. Then,
I think we should sit and we should do a quadratic equation over here tonight. I assure you. I mean, it's not a complicated equation. And I also actually, now I'm trying to make fun of them. It's really not fair at all. Because I have made this mistake about 5 times the last year, and like in various forms. But for God's sake, we can just, why don't you take, for example, the ungauge limit and find the, this small or large black hole? Couldn't I go off and find the Weiss-Nordstrom black hole, for example, in flat space? No. They do not asymptote to those, they just don't. Show you how these limits happen, but they don't. In the limit, when you're trying to go to the small black hole limit, small normally means, oh, you mean the black hole a lot smaller than the ABS5 scale. Oh, that means it's pretty much flat now, right? Well, unfortunately, the way it happens is that the black hole itself gets so small that it literally has zero area as you go to the flat space limit. You don't get anything interesting. You don't get the Larsen. Yeah, anyway, so say that this has been very frustrating because all of the simplicities you could propose and that people have proposed, and occasionally even have said are obvious, they're not right. You know, there really aren't many simplifications. There are reasons people don't do these computations. They don't have nice answers. You know, but that's not the same as saying one should never do them, right? Actually, quite the contrary. It's sort of the, oh, I see. So don't call them trivial, right? So what's the status? The exploitation of this entropy function is principled. The output is that we know the entropy as function of the charges and these Fi parameters. This story generalizes to various kinds of corrections, R-squared corrections, quantum corrections, but the computation, I think you would agree, is not illuminating, even though it is principled and gives very explicit formulae. One thing we do, and a few other people do, actually maybe only one other paper, is that, well, I wrote these formulae out in explicit form because I didn't want to introduce yet more notation. It turns out that if I combine these variables into complexified variables, it actually would end up going a little bit more smoothly. I would have only half as many equations, they would be complex, but they would look kind of nicer. Basically, think about it as in, there's an electric field. Oh, doesn't that naturally have an IB? Yeah, it does. And combining the two together is actually some way of writing these formulae ways that are kind of much more canonical. So that's one of just sort of the tricks we're finding. But I really want to avoid going complex, because then people are going to tell me that, oh, you mean 4D special geometry, which is always complex. And I definitely do not mean that. That is a completely different story. So, at any rate. But our objective, starting with this, was to understand things in space-time better. Well, for that we have some comments, but I must say, we're frustrated. So the BPS mass here, well, was roughly speaking the sum of charges, with some potentials in front. Sorry, they were called phi now, that should have called them x. The star refers to the horizon. But also in this context, actually the mass is not just this linear combination of cubes, basically the sum of cubes. There's also a mass. There's also an angular momentum. So it's a sum over all charges, if you will, or even angular momentum is included. So the first law, if one is near these things here, looks as follows. When you're near extremality, we have a temperature. The first law looks like this. TdS is dm. We obviously have something about charges changing, omega for J changing. This thing, if you rewrite it to prepare it in such a manner that you're ready to go to the BPS limit, you would say, oh, mass, maybe I should make it mass over the extremal mass. I should make phi here not be just any old electric potential. I should make it above and beyond the horizon potential I just found. I should make the omega above and beyond the omega star that I just found. So the way you go to extremality is you divide over by your temperature. And then you get the first law that we can reasonably call the first law of the actual BPS black hole. And the thing I'm trying to emphasize here is something that indexed people sort of would know. They would say, oh, yes, as you take the extreme limit, this thing here, which is a difference between potentials, you kind of divide over by the temperature and take the limit. This thing here takes a finite limit. So this phi here goes towards phi star, t goes to 0. This gives a finite limit. But what I want to say that the computations give, and give rather clearly, and sort of, is that, well, that limit here, these were electric potentials. This is what appears in the usual first law. When you then divide by the temperature actually appears in a way it's 0 at the horizon. But one way to think about these electric fields, these phis here, is that, well, they're kind of turned off at the horizon, but they increase linearly away from the horizon. The temperature is 0 at the horizon, but if you were to put in a would-be temperature a little bit outside the horizon. It also goes linearly. So therefore, one way to think about these things here is that they're not really just a thermal derivative of these potentials. Think about it instead as the radial derivative. That way, you'll be much better off and understand that, yes, this thing here really is the electric field. The electric field. So therefore, what the equations sort of give you is that you were taught that non-VPS stuff, near VPS stuff, things should depend on potentials, but what you're sort of being led to is that the only, whether you actually microscopically try to deal with indices and these potentials here, well, from the space-time point of view, you see that the derivative with respect to the temperature of the potential really is the electric field. Right? And you should think about this T dependence here as actually being a radial dependence in sort of physical space. And therefore, what you have at the horizon is that you have electric fields going out. You do not have potentials. That's just a feature of the VPS limit, is that the potentials themselves are just fixed boring boundaries. In particular, the omega here is 1. The horizon moves at the speed of light. That's not the interesting thing. You can't change it and use it as a control parameter or anything. You can go a little bit outside and say, yeah, but what was the derivative of that with respect to the radius? Oh, that is my control parameter that I can use to say that I want to change J while staying within the VPS surface. So this is one of the sort of things that we're interested in, was we're trying to find space-time interpretations of some of the various equations that we already knew were true, but at least I have not quite paid attention to the fact that these things, I certainly knew that you should divide by the temperature and so on, but that this really is a radial derivative, that right on the dot really gives the electric field, and that this then is the field that is dual to the electric charge, with all sort of pi's and 2's and whatever, correct. So at any rate, there's a whole story here about VPS thermodynamics, and there's written many pages on this, we've done many, many plots, but I think not, it's interesting to vary these various parameters, and actually explore this law here, and has very little has been done on it, actually. The VPS limit, people usually do near and then plot things sort of as they go closer, whatever. But it's actually nice doing it at the limit, and that gives a better understanding of the large and small branch and so on. They really are smooth in the limit. Yeah, so that was what I just said in words here, that my electric field here, remember my potential really is this. Oh, that means my potential kind of is 0, but the derivative of my potential is not 5 dimensions r squared, so I can put the derivative with respect to, so this becomes this. Similarly with this, my velocity field. Actually, I've gone to a frame where it doesn't move at all, but the derivative, as you go outwards, moves differently. So radial derivatives and thermal derivatives, they're equivalent, and that has many advantages. And this also gives a connection, incidentally, why these parameters here are the ones that appear in the scorch. The temperature dependence is taken out. Anyway, so I should probably say. So any questions here? That was sort of the final comments on just at the horizon. The standard computation, I think, we certainly have references, the one you mentioned, but sampling often is mentioned in this context, whatever, but I believe all of them have things we were unhappy with, certain signs turned not found right, or whatever.
Is there a scarcity story for these?
Yeah, well, so maybe, but so by courtesy of T, what normally is meant in asymptotically flat is that there, in fact, that's a good example of what we're saying. There's, so this constraint here, people, it looks unfamiliar. Say, why haven't I seen this before? Completely weird, gotta be a mistake, you guys are wrong. Actually, think about it. What happens in 4 flat dimensions? Well, you learn first about Brightstone-Northstone black holes. That's your first example of, well, could you make it supersymmetric? Yeah, you could. And I could do it without doing any kind of tuning of parameters, whatever. That's false. You definitely tune the parameter. You put the angular momentum to 0. That was your constraint. J equals 0. It was so simple you might not have noticed it, but there was an extra constraint. It's still something that couldn't I, for general Q's and J's, find an extremal black hole? You could. Are they supersymmetric? No, except if J is 0. So therefore, the supersymmetric ones are codimension 1 within the set of extremal black holes. Alright? So yes, specifically then if I go to the other limits, I don't want charges at all. I want just mass in J, that's very non-supersymmetric, and the black holes are really horrible, but you know, you have what you have, you do have an ADS too, and then you can run some issues with boundary conditions there and do a Brown-Hinault type of formula for that, which is not as secure as the Brown-Hinault formula, but is okay. And so that's the full extent of what we know about Kerr CFT. And is there a corresponding story for would there be a corresponding story for the non-supersymmetric guys here? I would say no, we don't have such a story. But it's a fair problem to ask. I'm assuming that things somehow work out, but only in part because they aren't that strong asymptotically flat in the first place. I mean, the numbers that have to work out for this to be a success are not really that hard. It's sort of, you know, I mean, sometimes when you get complicated functions that lead to other complicated functions, you know, this might have gone wrong, but these ones, you know, I don't think so. So, at least I have not really. I think people are not willing to try hard here. And you know, you can see these are the BPS ones, the corresponding extremal but non-BPS. They're way more pleasant. And this is unpleasant. Did I see another question? All right, so this was all at the horizon. Now we want to think about the flow. How does that work? Well, first you should go back to the Lagrangian I wrote that was basically an effective Lagrangian. It was really the Lagrangian evaluated on the ansatz, but evaluated at the horizon at a particular point. So I got this Lagrangian type of function that was just a number. And once you extremize it, well, you get algebraic equations. Well, now you should repeat, and you get something at any radial position. The result actually looks very similar to what I already wrote down, because that thing really would be there. You just take all these functions and say, oh, they could be functions of R. And all you need to do is to add certain kinetic terms, because you know, those derivatives were the ones that had been ignored. So you should add them in, and that of course means that you get basically a line in that already unitizing function, and now you should extremize, and that means that you get differential equation, you know, instead of algebraic equations, and differential equations are, you know, hard. So, but the next step you could do is to say, yeah, but there was another thing, these electric fields and magnetic fields, and so on, I need to change them for conserved charges. Now the principles for the flow are perhaps a little bit less obvious, but in order to extremize and get something that sort of, at least for us, is smoothly continuing into the, you know, extremization principle at the horizon, we would like to use some conserved quantities. Another way of stating this is that what we have going for us as we're trying to find the flow is that we know these supersymmetry equations. That's nice. We know supersymmetry variations, we put them equal to 0. But what we really need is that we need more data than just that. We need equations of motion. These equations of motion are hard to find. The second order, the best ones to get are actually the ones that correspond to conserved charges. So, almost everybody who compute expressions for conserved charges in general relativity or in ADS-CFT, they are computing asymptotic expressions. At infinity, there's a general set of ways of figuring out what's the angular momentum. It's not always easy, actually. You read off fall-off conditions, and you find some divergent angular momentum, then there's some local counter terms, and you subtract off, and whatever, you find something for the charges. It takes a bit of a song and dance there, and finally you're happy, you figured out what the Q or the J is. That is not what I'm asking about. I'm asking something that's a bit more general. I'm saying, look, Q's and J's, don't they correspond to some kind of, you know, flux interval that I should be able to compute anywhere in the middle? You know, it should just be the same everywhere. It should be conserved quantity. It's got to be something that I should compute specifically using a near-horizon method or specifically using a far-away method. And it's amazing to me that I checked a whole bunch of just GR books just for Kerr black holes to say, where do they actually compute this parameter called J? It's in fact the angular momentum in the Kerr-Newman, you know. Every single book I could find asymptotically. Let's expand at infinity, let's find medium mass, whatever. You say, no, but you guys, for example, in Sean Carroll's book, he finds a formula that is supposed to give angular momentum for any r, and he says, oh, let's just expand it because this is hard. The formula doesn't work at all r. It only works at infinity. So the formula is just wrong. Poisson's book is the same. Let's, for simplicity, expand at large r. It is simple and it is true, and it also makes the formula right. So at any rate, this thing here is, of course, just something that one should just follow the slightly better folks like Walt or something like that, where you have to update things. And so the another Walt procedure is that, look, we need to find conserved charges. And they should work anywhere. Well, how do you do that? Well, you do it like the neutral procedure. You vary the Lagrangian, and you get a term that you would say is what we normally call obviously the equation of motion.
This works because you have K vectors everywhere. In general, you might only asymptotic K vectors. And that's the reason why one does things. So because you're working with supersymmetric solutions, this is something that makes sense, but it wouldn't make sense otherwise.
It is fair.
The GR would say.
No, it is fair that if I want, study hydrodynamics or whatever other stuff, then yes, absolutely, I agree. But I would say that for these purposes, though, it's really important that I try to figure out, let me simplify basically my equations of motion. And the first thing you ask, any conserved quantities by any chance? When you have complicated differential equations, that's a good start. I'm saying that, I feel we have to do technology here. Find the equation of motion when you vary, but in the process, you always get, as we know, d of something. That something is called the pre-symplectic potential. At the same time, you also know that since we are by assumption saying that this variation here is not just any old variation, it's something that is a symmetry direction, maybe either a gauge field or a gauge symmetry, or maybe a killing symmetry, but either way, it has to be something that's a symmetry, so that means that, actually, it's just got frozen, actually. It seems to be frozen. No notes, no thanks. Just popped up. So, and anyway, so because it's a symmetry, the Lagrangian is d of something, because it's really the action that has to be invariant. That's what it means that's a symmetry, but the Lagrangian itself was perhaps not invariant, so it's d of something. On the other hand, if you actually go and vary a Lagrangian, you get the neutral equation of motion, but plus a total derivative. That total derivative is the pre-symplectic potential. And then when you go compare these two different guys, you find that did I not? Is there an equation missing? Oh, anyway, seems to be a slide missing maybe, but whatever. The upshot here is that if you compare these two different things, you find that the difference between this JC here and the pre-symplectic potential certainly is going to be closed, at least locally. Therefore, you have a conserved charge and some kind of abstract formalism here, but you obviously need to then say, well, let me go and actually work it out for these charges I'm interested in. And so on. What are these weird things that we may or may not have experience with, but most of us don't have much experience with? Oh, and besides, you want to be careful with your Chern-Simons term, because the whole thing that is the principle when you start with the other procedure is that, didn't I say that the action should be invariant, not the Lagrangian, just the action? But with the Chern-Simons term around, it's not even invariant under, the action is not even invariant under gauge transformation, so that's a problem. That's where there's a principle that you should add a suitable extra charge, a suitable extra derivative in such a way that your action with this extra derivative really is invariant. Then you get a conserved charge. There's a similar but different maneuver for the angular momentum where you have to be careful that you don't mess things up. But the upshot is that we have formulae for radially independent charges. They're written, regrettably, in a slightly different notation. These B's here, you should read as a B previously or whatever. But the upshot here is that this is the kind of charge, electric charge, that's a function of the geometry. U2 was the squashing parameter, this was an overall radial parameter, whatever, these were the scalar, stuff like that. So if you were to know all these different things, they're obviously going to be radially independent functions. And the statement is that this thing here has to be independent of R. Each of the terms in it depend on where you are, but as a sum, they have to cancel out. Same with this J here. At infinity, sure, this is going to give the standard formula, but it's actually the same everywhere. And that gives you then powerful constraints on these things. Before you've actually looked at the equations of motion, that it better be that I have these integrals of the equations of motion, right? And it really corresponds to having taken these Q and J as flux integrals, and then, well, do the flux integral over a suitable sphere that has some area that is dependent on these various parameters, because we parameterize the entire geometry. So this is what we can think about as saying we have solved a few of the equations of motion. Well, the word go before we actually try to start hard. Symmetries help us. But this is sort of not exactly just the usual Gauss's law. Right? This is turns on, turns, oh yes, and it rotated. I was kidding you when I said it was just a Gaussian flux integral. Of course, it's squashed. Actual curved surfaces and stuff. But it's not something that, ought to scare anybody, really. It's just, oh dear, yes, right. Now I understand why some of all these things weren't already done as simple exercises in kindergarten. But, yeah, because, At any rate, we still have a whole bunch of equations that we need to solve. We have Killing spinor equations that give us some flow equations. These are linear equations. That was just as Gabriel was saying. And one of the things that people sometimes forget is that supersymmetry is insufficient to solve equations of motion. If you just take a solution to these ones here, some arbitrary solution, if you were good enough, just integrate these guys up and find the arbitrary solutions to these equations, that will not be sufficient to solve all the equations of motion. Often we say, oh, the computer just managed to find the supersymmetry variations here. That would kind of be the square root of the equations of motion, roughly speaking. So integrals to these, you plug them into the equation of motion, it has to work. That's false. You do need some equations of motion. Basically, they are integrability conditions corresponding to taking two consecutive supersymmetry variations, and in order for them to close, you get bosonic equations, which are actually some of the equations of motion. So therefore, you have to, it's mandatory, that you actually go and find some the data from the equations of motion. And what is the data you need? The bosonic data, in order that the supersymmetry variations in fact close, they are the Gauss-Hall constraints. In other words, those that I had just found. These are, you can think about as having already integrated some of the equations of motion. This is really an equation of motion. It's integrating the Gauss' law. It was technically a second-order differential equation that was integrated up in favor of the first-order differential, and that it had to be constant. So therefore, having integrated up this conservation law, I've actually used an equation of motion already. I solved it happily by symmetry. And therefore, these equations, together with the conservation laws, form a complete set of equations of motion that, in fact, is enough to find the solutions. And so one of the things we get out of it here is to clarify a little bit maybe what is the minimum thing you need for these things. Of course, then the next thing you need to do is to take this Lagrangian that depends on R that I didn't actually write. You need to take the Legendre transform to get into something where you preserve where the charges, with electric fields are being eliminated in favor of conserved charges. And then, once you've gone to an ensemble, which is actually what we call the Ruthian, basically the Lagrangian with fixed Q's and J's, that one is guaranteed extremized if just I take my supersymmetry variations. What we're still trying to show, and have not been able to, but I don't think the other guy did that either, was to recover the one thing that we think is true is that the final solutions it should be possible to write them as gradient flows. So this is the one thing that I'm still conjecturing is surviving from the ungauged to the gauged case, is that the solutions should be, there are certain solutions to first order differential equations, but are they also gradient flows solutions, basically, so generated by scalars? And I think the answer to that is yes, but yeah, students are not used to it. Anyway, so work is still in progress, and thanks for your attention. Yeah, it's very right.
If I may just comment on this last statement you made.
The work is still in progress?
No, the previous one.
Okay.
Gradient flows. As far as
I
I
assure
remember, Gianluigi et al., now that is in 4 dimensions, they
Yes.
did write these equations as gradient flow equations for some sort
Yeah,
of...
yeah. Now you do remember, right? So yeah, they do some 4D stuff. That's right.
Yeah,
but did they? But you also mentioned they did 5D.
No. My
Okay.
comment was in 4D, but I
Okay.
believe
Yeah,
it
but that's
will
right.
go through.
So that's right. So they do some stuff in 4D, and I don't quite remember. Yeah, so I don't think we actually completely check out everything. And, it's but we found that there were any pieces missing various places of literature that at least we couldn't find. And, this is how it often works, right? Somebody does stuff, but as part of some development, usually then there's a second generation of things that does a little bit smoother and cleaner and whatever. And it seems like these gauge solutions, it didn't happen. There was only the first generation of versions that was, good. I'm not saying they're doing bad work, I'm just saying that usually it gets polished a bit better and things were sort of, at least, I can't find many of these things. And yes, this one we did, I guess, 4-dimensional. And then is everything good there? I don't recall. Maybe, probably.
The same?
Yeah, probably. I mean, but how did they do with the conserved charges, for example, or whatever? I don't recall. They don't have transition terms, but on the other hand, they have a much more complicated.
Well, they have magnetic charges, so,
What?
so they have magnetic charges. They're in 4 dimensions. So,
Oh no, that's these were the magnetically charged black holes. They're much simpler, right? So they're not rotating. That's cheating.
Not really. Look, there's going to be a preservation of difficulty here between 4 and 5D. So in 4 dimensions.
But I do think that these ones that are purely magnetic, the ones that are.
Theirs was totally general. There was
Okay.
no assumption about.
But did they have any momentum?
They were BPS.
Yeah. But there are some special ones. There's some special ones that are BPS where there's a constraint between just the purely magnetic charges. And those ones, also on the microscopic side, are very, very different in their microscopic. They're topologically twisted, basically. Right? So were these the topologically twisted black holes, or were they the other
No.
ones?
Making a generic statement,
Okay.
they had a generic they looked at generic configurations, and they had the first order Fourier equations in terms of some generalized superpotential, which used fluxes and Fourier-Liopold things. And this was a rather complicated object. I'm sure it's there also in 5 dimensions, but it's.
I remember this, but anyway, it did not have what we were looking for. But now I remember that. Look, there are many people who did good work, but surprisingly to me, there are many holes. I mean, there's holes as in not them doing wrong things, but examples that wouldn't work out and stuff like that. Features that weren't included that should be included because you need them. And here specifically, I was interested in this UV to IR flow, and that this entropy extremisation thing has gone. It's often confusing, actually, exactly if people get the charges correct, as in those that you read off on the horizon. Are they really the same that you would have found at infinity? And at least I have had my concerns, but now I'm no longer concerned. So, yeah. But I haven't looked at the data papers. I mean, we referred to it, but it was 40 papers. I can't compare equations. Sorry, no disrespect. So any more questions?
Okay, second one.